All right, so everyone can hear me? Yes? Thumbs up? Great. So hello, everyone. Welcome to the monthly Berlin ML Meetup. And this month, today, we have one speaker, and that is Simon Wiedemann. And he's going to be talking about compression and efficient processing of deep neural networks. He'll give much more detail about that, but I'll give a brief bio of Simon. So Simon has worked for the last 4 years at Fraunhofer HHI as a project manager and research associate in topics related to efficient computation and processing of deep neural networks. He's published several papers on the topic, and he's one of the main contributors to something called Deep CABAC, CABAC. It's a compression engine for deep neural networks. And it's selected as a core technology for MPEG's upcoming standard for neural network compression. And he's currently wrapping up his PhD and is going to be starting his own company this month. And maybe he'll tell a bit more about that too. And the goal there is to reduce the costs of running large DNNs in production. So with that, Simon, please take it away. Thank you for joining us.
Sure. I will start sharing my screen then now. And if you guide it to the slides, let's see. Play. Can you all see my screen now? Oh, perfect. So yeah, thanks Trent for letting me speak at the Berlin Machine Learning Meetup and for letting me give this talk and giving this nice introduction. As he said, yeah, I actually just 1 week ago quitted Fraunhofer to start my own company, which is related to this topic that I'm going to talk about today. And what we're going to do in Nano AI, it's called, so I would encourage you to check out the landing page. We're going to provide optimization algorithms to everyone so that they can optimize their deep learning models to run much more efficiently, either on the cloud or on end devices, and like that reduce drastically the cost of running these models. But today, actually, I'm going to talk about more in general, more from an academic point of view on this topic, and talk also more in detail what some of the super interesting research things that we have been working on at Fraunhofer and my colleagues over the past 4 to almost 5 years, in this field of compression and efficient processing of deep neural networks. So yeah, without further ado, I will just jump right into it. So the problem is that in our endeavor to try to solve more and more complex machine learning tasks, machine learning practitioners have been equipping the models with an ever-growing number of parameters, so much so that they have been growing exponentially over time. And as you can see in the upper graph. But the thing is that processing such large number of parameters takes a huge amount of resources in terms of memory requirements and speed. So they're very slow, and also they consume a lot of power. And the thing is that if you see in the lower graph, the hardware innovation progress is not able to keep up with this trend. So that means that inevitably, we are going to reach the point where training and performing inference of state-of-the-art deep learning models is going to become economically, technically, and environmentally unsustainable. There is also a growing interest of running deep learning models on resource-constrained devices like phones, microcontrollers, cameras, and smart home appliances, etc. Because doing so provides a series of advantages as compared to running it in the cloud. Because, for example, then end users don't have to share their data to third parties because you can run and analyze the data on their device. It also gives advantage in terms of latency, power consumption, storage, and also you can reduce the cost because you can run these models on much cheaper hardware platforms. So since this is such a big topic and an ever-growing problem, let's say, there's been a ton of work over the past years from academia and industry trying to kind of tackle this problem from different angles. And here I just wanted to give a really quick and brief overview, and so that you, if you are interested later in this topic, you know, I don't know, you can dig deeper into the different aspects of, you know, the general field of efficient processing of deep neural networks. Yeah, so for example, one topic which is super interesting is people have been trying to look how can we make training of models much more efficient. And they have been studying, for example, methods that, you know, like try to come up with better optimizers. So meaning that you can train them with made to convergence by having much lower number of steps, for example, or requiring much cheaper computations for entire training procedure, etc. Then there's this whole field of distributed training, which means, okay, I don't know, 50 GPUs or 50 CPUs. How can I distribute the training across this across this devices or these nodes, so that the entire training of the model can be performed much more efficiently. Yeah, inside this topic is also the communication efficiency of the model across these distributed nodes. Yeah, this will be the topic of training, efficient training, but there is also this other huge field of how can we make the inference of deep learning models more efficient. And there would belong, for example, new-architecture search approaches where, or maybe more concretely, constrained new-architecture search patterns, where you don't not only try to come up with a model that has high accuracy, but also at the same time, this model that you try to find needs to satisfy certain resource constraints, like it doesn't have to consume more than 1 watt of power or something like that, or it needs to run in real time, etc., etc. Also in this field belong this technique called distilling, which is trying to distill the knowledge of a larger and better performing model down to a smaller model and make it, and like that increase the smaller model's accuracy or prediction performance. And also a super interesting topic in this field is dynamic networks, which are special type of networks that have some sort of mechanism of identifying how much computations they need to perform a good classification condition the input data. So for example, if you have really easy input data that you know, doesn't need as much computation to have good prediction performance, then they use a smaller parts of the network in order to perform the prediction. And if there is more complex input data, then they use larger parts of the network. And then there's the third field, which is the entire, you know, hardware people and system architect people that try to come up with special hardware device platforms that can run these models and train these models much more efficiently. And this belongs, for example, TPUs, FPGAs, or specialized ASICs, or in-memory computing, etc., etc. But today, I'm gonna actually, because you know I cannot talk about everything, so unfortunately, so I'm gonna focus on techniques that I would argue lie kind of an intersection of those three fields, because these sort of techniques can be applied to make training more efficient, as well as make inference more efficient, and as well as create specialized hardware that can run this and train these models more efficiently. And yeah, concretely, I'm going to talk about pruning, quantization, and compression. But I'm going to focus more on the topic of size. So how can we apply this kind of techniques to reduce maximally or as much as possible the size of the neural networks? Because this is one of the biggest problems right now. That we're currently facing. So yeah, I will just try to jump into it. So pruning, I think most of you already know it, but I will just say it. Also, yeah, pruning is also sometimes called specification, and it's all this class of methods that basically just try to remove parameters out of the models. It's super simple, the concept, but there are two key questions to ask: is okay, how can I remove parameters of the model in such a way that at the end of the day, I actually have higher efficiency in terms of size reduction or speed ups or reduction in power. Also, another question is, how can I remove the parameters of the model in such a way that I can maintain prediction performance of the model? So, because removing parameters, incurs damage in its ability of predicting the data. How can we do that without damaging the model's inner workings as least as possible, at least? So regarding the first question, the fast answer is, okay, it depends on the hardware where you want to run this. I know it's a little bit unsatisfactory, but that's just unfortunately how it is. The thing is, just removing parameters in a seemingly random way, or in a seemingly or in an unstructured way, so that the zeros are just distributed in a seemingly random manner inside the model, cannot be really exploited by common hardware platforms like CPU and GPUs, because these hardware platforms really need to have some sort of predictability regarding how to process the parameters in order to run efficiently. Yeah, that's why actually there is because they are not tailored to process such type of unstructured data. There's been this huge field of people trying to build specialized ASICs that actually can support the processing of unstructured graph neural networks, and also also the study how can we configure FPGAs so that they can run these models, unstructured models. What people have been doing then, instead of just removing zeros, just removing parameters without following any structure, is they say, okay, I'm going to do it in a more structured manner. So, for example, the next step would be I remove the parameters in blockwise manners. So if you think of a layer of a neural network and a tensor, so I remove just sub-blocks. And this can be exploited much more efficiently in CPUs, for example. You can actually then see huge speedups if you do that in this way on CPUs. Or if you want to run it on GPUs or TPUs, which require or which are based on massive parallelism, then you really need to have your parameters highly structured, and that's why the technique is applied in such a way that you actually remove entire neurons or entire filters of the network in order to get efficiency. So this is to the efficiency. So like, how can we maintain accuracy if you do pruning? One of the most common algorithms out there, I would say, and arguably the most common, is by doing an iterative approach. Also because it has been proven many times and published that this approach actually is quite effective, and you can attain quite high sparsities if you apply this algorithm. And it's super simple conceptually. So you have to follow these 4 steps, which is first of all, you decide for a pruning strategy, either unstructured or structured or blockwise structure, whatever, depending on the hardware you think you're going to run your model. Next is you say, okay, I apply some sort of criteria that kind of makes some sort of estimate about how important is each of the parameters of the neural network for the particular task that I'm trying to solve right now. And once you have this kind of importance score assigned to each parameter, you sort them accordingly and then prune away the X% least important parameters. And then the non-pruned away parameters, you fine-tune them with, I don't know, some training set or validation set in order to recover for the accuracy loss. And then you repeat this process for several iterations, and then you attain a highly sparse or a network with much less number of connections than before. And in this whole algorithm, one key question, of course, here is what kind of criteria to use, because the outcome of your method or of your is totally based on that criteria. And there's been many things proposed in the past. One of the most popular is weight magnitude. So basically, this consists of saying, okay, weights that are larger in magnitude are more important than the other weights. And super simple, but yet actually quite effective. But others have tried to actually come up with a little bit more better criteria, because weight magnitude doesn't even depend on the input data. So you would think, okay, I can maybe come up with a criteria that kind of takes the input or the data that I'm looking at or my model is looking at into account in order to estimate the importance of each parameter. So some people have, for example, proposed the gradient-based approach. They look at gradient of at each parameter, and then assign the importance of each parameter depending on how big the gradient is there, and many other approaches. But if you think about it, a good criteria, if you think into this problem, you can come up with some properties that a good criteria should satisfy. And yeah, I've listed them here. So one is actually, if you estimate the importance of the parameters, then the score that you assign to each parameter should be global, in the sense that it should reflect the importance of this parameter throughout the entire network. Magnitude-based approach doesn't satisfy this condition or this property, because what is a weight that has large magnitude in one layer doesn't mean it's more important than the other weight that has less magnitude in the other layer. And that's why this weight magnitude approach is a little bit not nice to use in practice, because it induces a lot of hyperparameters and etc. So it's kind of not so handy in practice. Why there's this motivation for finding other criteria that actually have this property. Also, if you think about it, another property would be that these importance scores are conservative in some sense, because in the sense that, for example, all different layers should have kind of, if you sum the importance of scores of the parameters of each layer, they should kind of have the same number, so let's say 1. So the importance of each layer should be conserved, because if you, for example, if you think of feed-forward neural network and you remove one layer, then the entire network is destroyed. It doesn't work anymore. So that means that each layer is basically equally important. Of course, you have some exceptions when you have skip connection and things, but this conservative property, or basically this importance to reflect this property that each layer is almost equally important, for the classification task. Computing this criteria should be, of course, data and compute efficient, ideally. And this is what we actually have published recently, one of such pruning criteria, which was motivated by the interpretability domain. And it's called, the paper is called Pruning by Explaining, another criteria for deep neural network pruning. And what we have done is, we have applied what it's called a relevance score to each parameter or neuron in this case. So this particular, importance score, it's called layer-wise relevance propagation. And it was firstly invented for interpreting which kind of pixels in the input image are most relevant, or were the most relevant for the classification. That's, for example, the classification in this case. So you have an input image of a cat, and then it's classified as a cat by the model. And then you ask the question, okay, which input pixels were the most relevant for the classification? And then if you calculate this relevance scores back to the pixel, to the input pixels, you see that the contours are more highlighted in the eyes and the nose and things like that. And this highlights you, okay, these parts of the input were the most relevant or the most decisive for the classification task. However, as a byproduct of this algorithm, you get a relevance score also for each neuron of each parameter. And the nice thing of this importance criteria is that it's conservative and it's global, and it has all of these nice properties that I just mentioned before. And if we compare it to other criteria, you see that actually for the same pruning settings, you get much higher accuracies than if you apply the other stuff proposed before. Especially at ResNet 50, you get much higher accuracies than if you apply, for example, weight magnitude-based or gradient-based approaches. And also these results reflect that. Here, in this experiment, what we did is to say, okay, we're going to take ImageNet models, and we are going to try to figure out which components of the models are especially important for the cats and dogs classification. And then a good criteria and a good importance score should reflect this subcomponent of the network better. And that's why you should be able to prune much more of the network before the functionality breaks down. And this is what it's shown here, actually, quite nicely. If you apply LRP criteria, you can actually prune up to more than 95% of the model without harming its prediction performance for the subclass of cats and dogs. If you take the pre-trained model that was trained on 1,000 classification tasks, this would be a little bit quick overview of pruning. Now we're going to jump right into quantization, which is another technique to make your networks smaller and more efficient, may allow them to run more efficiently. And this thing is called quantization, which basically, in more machine learning terms, it's just another word for saying clustering. So what you're trying to do with quantization is to take the neural network's parameters and cluster them into smaller size buckets. And why this is good for performance? It's because when you cluster the parameters, you can compress them also more. And depending on the clustering method you apply, you can also save a lot on arithmetic, on computations. You can perform cheaper arithmetic operations than if you would use, for example, floating point or the standard representation that was used before. Just to give a good example of how this would work, if we, for example, constrain the clusters to be equidistant to each other, if you look at the MAC operation, which is activation times weight plus activation times weight and so on. After quantization, I don't know if you follow the equation, but at the end of the day, you can reformulate it and see that you can actually convert it into a MAC operation of that only requires integer arithmetic. And integer arithmetic is at least 3 times cheaper than, for example, floating point arithmetic. And this is one of the most common techniques nowadays applied when it's when people say that they're quantizing their models, especially, for example, in TensorFlow Lite, or TensorFlow allows you to do this kind of optimization. But maybe what is more important than the saving on operations is actually the compression part, because actually one of the biggest drivers of resource consumption in hardware is actually the movement of data. So the reading and writing data in and out of memory. So if you can compress the parameters a lot, then you need to read and write less amount of bits. And that's why you can save a lot on power consumption and increase the speed, and et cetera, et cetera. So that's why also I'm going to focus a little bit more on this topic and this talk. But just to give a quick overview, what kind of compression approaches, or some of the most common compression approaches that are out there. One of course, the most simple is if you constrain the number of clusters to be small, then you also need less amount of bits to represent each parameter. For example, in the most extreme case, if you only have 2 clusters, then you just need 1 bit per parameter in order to represent its value. And as such, you compress by 32 times at least, the the model. But if you want to go a little bit further with compression, you can apply a little bit or okay fancy lossless compression techniques, like for example the Huffman coding or just zipping them, etc. And this, depending on the hardware, of course, again, can also give you again further boosts and efficiency thanks to lowering the data movement inside the hardware. And and one of the works we have been doing so far is pushing this even further. And we have come up with a super fancy compression engine, which is called DeepKavak. And I'm going to dig deeper into this a little bit later. But before doing that, I wanted to review for you guys a little bit of fundamentals of source coding, or I just call it fundamentals of compression, because I think it's a little bit fun and an interesting topic, and it will help you also understand more how DeepKavak works at its core. What is compression? So if you, for example, take a look at these two arrays of bits, I think everyone, at least intuitively, would agree with me that the right array is more compressible than the left array. And the key thing here is to think that compression actually roots under the principle that the more you can predict your data, the more you can compress it. And this kind of principle can be actually quantified mathematically with, of course, probability modeling. And Shannon actually did it already in his super, one of the most influential works, I would say, in science history, history of science. So he said, okay, if we know the probability of a particular value or a particular outcome, then we know how many bits we need fundamentally in order to or represent it, or how much information this outcome contains. We can calculate it precisely which is the -log2 of the probability. And just to give you an example, if we, for example, assume that in the above right-hand side array, that the probability of the zero that the outcome of the zero is 87%, we can compute the exact amount of information that this array has, and it would be 4.7 bits, which is less than actually 10 bits. What if we would naively just represent this string as I just did it in this slide. So since this whole compression theory is based on knowing the probability of your data, of course the next question comes, okay, in most real world scenarios I don't know the probability of my data. And therefore you can, therefore what the entire topic of lossless compression it's all about is a little bit also actually goes into the machine learning, domain, or it's related. And you can state some of the most important properties that a lossless compression algorithm should have if you want to use it in a practical way on real-world data. One is what I call universality, which is basically any lossless compression algorithm should have some sort of mechanism that allows him to estimate the underlying probabilities or distribution of the data as good as possible. After doing that, you know how many bits you need fundamentally to represent this data. So it should have some sort of mechanism that outputs a representation of the data that has minimal redundancy. So it doesn't have any wasted bits to represent the entire information of the data. So for example, in this array before, we know that it's you only require 4.7 bits to represent this data. So a good lossless compression algorithm maybe would output a 5-bit string representing the entire content of this array. And of course, encoding and decoding should be as efficient as possible. One such algorithms, it's called Kavak. which is arguably one of the best lossless compression algorithms ever invented. And it's also the compression algorithm that is used in the video coding standards, H.264 and H.265. And yeah, now I'm gonna explain a little bit deeper how this Kavak engine works. Yeah, first of all, I just wanted to remind lossless compression always works on integers. So you always assume that your data is represented in integers because you assume that it has been quantized, because if you don't quantize it, you cannot compress it. And quantization, again, means clustering. And if you have clusters, you can represent each cluster, or you have a one-to-one map to the integer domain. Because of the clusters. So I'm just trying to clarify why we only have integers in this in this table and in this diagram. Said that, so the first thing that Kavak does is say, okay, I have some sort of mechanism or some sort of mapping, which is called binarization, that maps each integer value to a concrete and specific binary representation. And this binary representation corresponds to traversing a specific tree from root to the leaf. And this tree is where you insert as a I don't know, compression expert your priors about your data. So the better your tree reflects kind of some priors that you have regarding your data, the better your lossless compression algorithm at the end of the day will be. And this particular diagram here shows the tree structure of that is implemented in DeepKavak. And basically, I'm not going to go into details, but yeah, it goes up and down. And basically, it roots at the principle that smaller integers will be assigned with smaller bit strings. Because yeah, it was under the prior that most of the parameters will be quantized to 0, and then if the next number of parameters will be quantized to the number 1, to -1, and so on and so on. So this is the prior we insert in this compression algorithm. After having this binarization scheme defined, how it works is as follows. For each of the edges of this tree, or each of these path points of this tree, it assigns a Bernoulli probability model. It assigns a probability model, which gets updated in an autoregressive manner upon seeing incoming data. So at the beginning of the entire compression step, it has it has no idea, and it assumes, for example, 50% that that the number 1 will appear 50%, the number 0 will appear 50%, so on and so on. But upon encoding more and more data, it will update its probability model, and it will become better and better and better at estimating the probability distribution of the data. And because it has a better model about the distribution of data, it can also compress it, therefore more. And it uses arithmetic coding for compressing the string of data into a smaller sizes. And yeah, like I would love to talk about it, but I don't have much time, so I will skip that part. Here's just to show an example what this kind of updating of the probability model allows Kavak, or in this case, DeepKavak, to do. It allows to adapt its probability model to really a wide set of different shapes of distributions. For example, this is the last layer of VGG16. And you see that it has quite a distinct shape, but Kavak is able to really to this form thanks to its updating mechanism. Now I've talked about the lossless compression part. Now I'm going to talk about how DeepKavak does the quantization. Which is also a little bit better, like I would say, a little bit more sophisticated than usual approaches. So since Kavak works sequentially in an autoregressive manner, it has this thing that at any given moment in time or in position or for any given parameter of the neural network, you know its size. You know how many bits you're going to spend for storing this parameter. And what it does then, the quantization procedure, what it does is says, okay, what I'm gonna do is I'm gonna quantize each parameter in such a way that it also take its size into account. So I'm not just gonna cluster, for example, to the nearest cluster center that I have, but I also gonna try to consider the amount of information I spend for clustering it into one specific bucket or into the other bucket. And this will can give you a big boost also in the compression gains that you can achieve later on, because you take the compressibility of the model into account while you're quantizing it. Here's just to explaining in the grand scheme how this compression engine works. What you do is you go layer by layer, and then you scan through all of the parameters and quantize them with a particular quantization setting, which defines the trade-off between the quantization strength and the compressibility of the model. Run it through the KABAK, you get an output, a size of the entire model, you decode it, you dequantize it, and then measure its accuracy, and swipe through a bunch of hyperparameters until you find your desired trade-off between the prediction performance and that you want to achieve for your model. And this works actually quite phenomenally well. When you, for example, in our paper, we show that, for example, for off-the-shelf pre-trained models for example, for a wide set of models or George vision, you can get up to 20 times compression. Without having to retrain or anything, just applying this algorithm, you can get 20 times size reduction. If you do pre-sparsify the models, so you apply pruning and then apply this deep KABAK quantization and lossless compression technique, so the three techniques at the same time, then you can get, on average, 50 times compression gains. And here's some concrete examples. For example, VGG16, without loss of accuracy, we've been able to compress it from 500 megabytes down to 8 or 8.7. For example, that has originally 16 megabytes. We've been able to compress it down to 1.3 megabytes only, and still maintain an accuracy of 75%. Which I think is quite nice. Like, under my knowledge, this is the smallest model I've seen so far that reaches such high accuracy. The BERT model, 10 times compression without losing really its prediction performance, and YOLO with negligible loss, also we can get more than 10 times compression. As Trent introduced before, Deep KABAK because it is such a good compression algorithm, it has been selected for the MPEC's upcoming standard of neural network compression. I don't know if, for those of you who don't know MPEC, this is the international standard organization that has come up with MP3 and the video coding standard like H.264 and H.265 that most of the devices out there use right now. And they are now working on a compression standard for neural networks. Then we also got fortunately, the Best Paper Award at ICML 19 workshop. Deep KABAK, you can use it. It's free to use on the GitHub. Well, not free for research purposes, free to use, of course, because it's in the standard. If you want to use it for profit purposes, then you need to talk to HHI. But you can use it for your research. It's open source, the code. It's there. You can play around with it. We've been able to do further improvements, reduce the complexity of this kind of hyperparameter search significantly, so that you only have one hyperparameter for that. Yeah, improve the quantization also because we implement state-of-the-art vector quantization now instead of just scalar. And we were able to increase the efficiency of training, especially in distributed training, like in the further learning use case, by reducing the communication costs of communicating the gradients of the models across different nodes significantly, yeah, on average on 23 times than if you would apply federated learning as it is. Yeah. So actually, this concludes my talk. I don't know, maybe I was quite fast, but I can answer any other questions you have gladly. And yeah, I would encourage you to. I've worked on many other topics in this field, also on efficient training methods, which we published in a recent paper. It's called the Backdrop and VPR 2020. And also other methods how we can reduce the explicitly constrain the training of neural network to explicitly reduce the information content and making much more compressible. But you know, in this talk, I don't know, I couldn't cover all of the topics. I would just encourage you to look up the Google Scholars or to reach out to me anytime. And I also encourage you to look out the InNanoAI landing page to see what I'm going to be up to in the next, in the next near future. So yeah, thanks for listening, and glad to answer any questions you have.
Thank you very much for your talk, Simon. It was a beautiful talk. Thanks for all the explanations. Facing the problem of deploying huge deep neural networks on a daily basis myself, I was, of course, very interested in hearing your research. Yeah, it's very impressive. The first and the most important question, I guess, is could you share your presentation?
Yes, of course. Yes.
Great.
That, I guess I just send it to you guys, the organizers, and
you can just put the link on the event page of this evening, so then everybody can easily access it. Yeah, that would be awesome. Thank you very much. Let's go back to pruning. So pruning is lossy, right?
Yes, exactly.
Then first of all, that Git repository you shared on your previous slide, does it also have code that does pruning?
No, this repository that I shared is just for applying the Kavak. Exactly.
Okay.
Just for, this is, just to re-stress, Deep Kavak is you take in any kind of model and then it outputs like the most compressed representation out there of the entire model. So this is what it's kind of the goal of this algorithm is.
Yes, but back to pruning. Is there code that or a library that does the pruning for you, or do you have to?
This not yet, I guess, but yeah, I guess there's the plan of publishing, because this is a very, very recent paper. It's like really, maybe 1 month ago on arXiv, and we're still working on a journal version of this. So like so
and can you say anything about the speed up that you get by pruning models?
That's true.
It depends on the accuracy that you want to have in the end, of course, but yes. Could you give a rough indication?
Exactly. Unfortunately, not real speed ups like measured on target hardware platforms, because this paper or this work was more about finding a better criteria for pruning, so that you can prune more without affecting the accuracy of the model. But also, I know that we can reduce much more the number of flops of the model with this approach than by applying, for example, other criteria. Which is just a very naive and indirect measure of efficiency, but nevertheless, it gives a little bit of an indication that this is for structured pruning, by the way. So structured pruning, if you remember, is this one on the right-hand side, that after applying this pruning algorithm, you can actually just, as an output, you get just a smaller model in general. And if you can prune more, I mean, at some point, you need to have more speed ups, right? But of course, it depends on the hardware, as you said. And I unfortunately don't have the numbers now. LRP-based pruning, yeah, I don't have benchmarks on specific hardware platforms regarding its speedups that can be attained with this approach.
The benchmarks you showed were all related to image data. Does pruning, as you described it, also work for text data?
It should work, yes, in principle, but you need to modify a little bit this relevance propagation algorithm so that it is applicable for text data and transformants because they have very special type of connectivity. But yes, of course, in principle, it works. And I think my colleagues who actually, are experts on this kind of relevance propagation approach, they are planning to extend this thing so that it is applicable to NLP models too. Right now, as we talk. So I think soon, I guess they will publish a code for that.
Cool. Yeah. Then let's move to the quantization. So the second part of your talk. I never thought of it as clustering actually. So thank you very much for that explanation. You already said that the code is available, at least for research purposes. I was intrigued by one little figure that you flashed on one of your slides. That was BERT. Now I'm not sure if I quite understood what you meant. You said BERT, so we're talking about a 1.2 gigabyte big monster that had but you had like on the right you had like compressed it to a mere megabyte, 45 megabyte. Did I understand that figure correctly or not?
Yes, you're right. But this BERT model was, there are different versions, right? I think this is the smallest, which is 433 megabytes.
Okay, but still, so, it's an order of magnitude smaller.
Exactly. Yes.
And so also an order of magnitude on the order of magnitude faster while deployed.
So the speed. So if you, this is another question. When you compress a lot like this, it doesn't necessarily mean that you get speed ups yet, because a little bit. So it's okay. I will explain a bit more. The thing is that when you have such type of kind of compressed representations, unfortunately, you require specialized hardware to really exploit the efficiency improvements that you could get thanks to this kind of compression, because you need to do decoding on the hardware because unfortunately on the compressed representation you cannot perform the computations that you need to do. So you need to do efficient decoding on the hardware, and at the same time take care of inside the hardware all sorts of data movement, and so optimize the entire computational flow inside the hardware in order to exploit this kind of compressed representations. But and unfortunately, CPUs and GPUs right now don't handle it, or there's no compiler for that right now. But especially the community that is working on the standard are working now on hardware implementations that support the efficient processing of this compressed versions of the neural network models. And I mean, if it becomes a standard, the hope is that sooner or later, almost all of the devices will have some sort of engine that can run this and support this the efficient process and efficient inference of this kind of models. And also just to point out that since this compression engine is based on Kavak, and since Kavak comes from the video coding community, where is it? Here. Already billions of devices out there, like all the mobile phones and all NVIDIA cards and etc., have already a Kavak decoding engine in them. So it's not, it's what I'm trying to say here. This is not so futuristic, let's say. So it's very close. So sooner or later, it will be implemented, I guess, and for the specific case of neural network inference. But yeah, right. It's still a research topic, I would say. It's still or a work in progress. So unfortunately, I cannot tell you the speed up or power gains that you can get. But the first step was, okay, let's try to make them as small as possible. We can get like reduce the computation, the power consumption, and increase the speed for doing inference after that.
Cool. Again, thank you very much for your wonderful talk. If Trent doesn't have an additional question, then why don't you wrap? And of course, good luck with your startup.
Thanks a lot.
And Trent, if you then take over the mic to wrap up the evening.
Sure. So thanks again, Simon, for the great talk, and Adrian for moderating, of course, and thanks to our audience for listening and tuning in this evening. And I guess with that, we will say good night and have a great evening and see you again in a month.